I scraped the stuff off the bottom, which was the burnt stuff, and that even tasted pretty good. So I almost burnt my tongue too. Okay, we're going to section 2 now. So section 2, we're not going to spend a huge amount of time on. There are two theorems. There's the Rolle's theorem and there's the mean value theorem. It has to do with the value of the slope of the line between 2 points. And it does require us to find the points where the slope goes to 0. So it's using the stuff we learned in the last last section. But let's just so Rolle's theorem, it's in your book. Don't write it down. I'm not going to ask you what Rolle's theorem is. But it says let f be continuous, which is a function. So it's a continuous function, which means there are no breaks in the function on the closed interval a to b. So that means it includes the endpoints, and differentiable on the open interval. So it has to be differentiable between a and b, but not at a and b. And it says if the value of the function at the beginning and the end of the interval, f of a and f of b, they're equal to each other, then there's at least one number c, some value of x, c, in the interval such that the first derivative has to equal 0. Okay, so let's explain what that really means with a picture. So I'm going to draw a picture. Just draw some arbitrary looking kind of function. So here's my axes. Excuse me. Okay, so here's my function. And this is some value of y. So we can extend that out. So if we draw a line from the x-axis to the graph, and then go horizontally over to the y-axis to find out what the value of the function is. So that's that. So this is x equals a, and this is f of a. And the same thing over here. You've got the value. You've got the x value, x equals b, and you've got this is also f of b. So it's not just two arbitrary points, it's two specific points where the value of the function at the first value of x is equal to the value of the function at the second value of x. And what it says is that somewhere in between the slope has to be equal to 0. So you can see that happens if I draw a horizontal line and I just bring it down to the curve. So right there, that's where the value of the derivative is 0, and that happens at least once between x equals a and x equals b, and that value of x where that happens is called x equals c. That's a specific case. So it's kind of like, what goes up must come down, or what goes down must come up. I think that's my simple way of explaining Rolle's theorem. The only case of where you don't go up and come back down again is if you were completely horizontal. If the function were just a horizontal line, and in that case, the slope would be 0 everywhere between a and b. But there's at least one point. I could make it go up and down and come back up again, so that the value of the function at the beginning of the interval is the same. So Anyway, that's Rolle's theorem. So the homework problems associated with Rolle's theorem basically say prove Rolle's theorem. So what they'll do is they'll give you a function, and they'll give you two values of x where the function is equal, and then you have to find out the value of x between the two where the slope does go to 0. And that happens as long as the function is continuous. If you had a vertical asymptote, then everything's doesn't apply anymore. Okay, so that's Rolle's theorem. I'm surprised I didn't do an example, but maybe I'll do in a second. Can't remember how I set this up. The second one is called the mean value theorem, and it's very similar to it, except that the value of the function at the beginning and the end of the interval doesn't have to be the same. So what it says is, again, the function has to be continuous on some closed interval from x equals a to x equals b, and differentiable on the open interval. In this case, it says there exists a number c, x equals c, between a and b, such that the slope at a point c is the same as basically the average slope between the 2 points. So this kind of, if you go back to physics, this is like the average velocity, and this is the instantaneous velocity. So it's saying that between 2 points in time, that the average velocity between 2 points in time is going to be equal to the instantaneous velocity at some point between x equals a and x equals b, or t equals a and t equals b. So that's what this is. It's like an average velocity versus a instantaneous velocity. So let me just draw a picture and explain what that says. In this case, what you do is you use, instead of setting the derivative equal to 0, you calculate what this value is, because you'll know the interval, you know the function, so you can calculate the value of the function. You get some number here for the slope, and then you figure out what value of c is such that the derivative at c is the same as the average rate of change for this particular process. Okay, so let's go back to 2 pages. We'll add a page. So pretty much the same as the last drawing, except the values of the function don't have to be the same at the beginning and the end of the interval. So here's my curve. So let's say it looks like this, and I'll pick that as my starting point, and let's pick this as the end point. So this is x equals a, this is x equals b. Notice it's a continuous function. It's also differentiable. And if I draw a line between these 2 points, what this is the slope of the blue line. And what it's saying is that the slope of the blue line, which is your average slope between the beginning and the end, is the same as the instantaneous slope at some point, at least one point. So again, right, that would be the point. This would be the value of x equals c, where the slope at x equals c is the same as the slope, the average slope from the beginning to the end of the interval. So these two lines parallel. This one you get from that equation. This one you evaluate the derivative at some value of c. So again, what you have to do in these problems is you have to figure out what value of c gives you a derivative, value of the derivative equal to the average across that interval. And again, it's not what goes up has to come down, but you know, if you go to a higher slope initially, to get back down to the other point, you have to go to a lower slope than the average. So initially, you know, before where there is this this point, the slope is higher than the average, and then these are lower than the average. And there's somewhere in the middle, it has to be the average. Okay, so here's a Rolle's theorem example. It says, determine whether Rolle's theorem can apply for a function on the closed interval a to b. If Rolle's theorem can be applied, find all values of c in the open interval a to b such that f prime of c equals 0. Okay, so the first thing is determine whether Rolle's theorem can be applied. Can Rolle's theorem be applied? So the questions are, you got to ask it continuous. Is it continuous? Question mark. Is it differentiable? And does, and this should be B, I guess, and does f of A equal f of B? Those are the three things you have to answer before you can apply Rolle's theorem. So, is it continuous? Let's see, who am I going to ask? Daniel. Is it continuous? Yeah, because it's a polynomial. Okay. Let's see, Elias, is it differentiable? Yes, because it's continuous. And so functions that are continuous are differentiable. Okay, does f of A equal f of B? Well, we don't know unless we stick the numbers in there. So let's stick x equals 1 and x equals 4 into the equation. So f of 1 equals 1 squared minus 5 times 1 plus 4, which is 0. And f of 4 is 4 squared minus 5 times 4 plus 4, which is 0. 16 minus 20 plus 4. Okay, so yes, check. F of A equals F of B. So those are the requirements that you have to look at to see whether Rolle's theorem applies. So now we know it applies. So if Rolle's theorem can be applied, yes, find all values of C in the open interval A to B such that f prime of C equals 0. So the second part of the problem, what you do is you take the derivative of the function, which is going to be 2x minus 5. You set it equal to 0. 2x minus 5 equals 0. So you get x is equal to 5/2. So the question is x equals 5/2 in the interval from 1 to 4. And Callie, is 5/2 in the interval? Meaning, yeah, is it between? Yeah, so it's halfway. It's actually halfway between 1 and 4. And that happens with, well, no, it doesn't happen always, but in this case it does happen. So what this is, because this is true, because there is a value of x between 1 and 4 where the slope equals 0, then we've confirmed that Rolle's theorem applies for this particular case. But since it's a theorem, we know it applies every time. So anytime you have these three things happening, then Rolle's theorem applies. There should be some value of x between A and B that the slope goes to 0. Okay. The next one is an application of the mean value theorem. So it says determine whether the mean value theorem can be applied to f on the closed interval A to B. If the mean value theorem can be applied, find all values of C in the open interval such that f prime of C equals f of B minus f of A over B minus A. So there's one less requirement for the mean value theorem. It has to be continuous. It has to be differentiable. How are we doing on the candy? Okay. Haven't eaten it yet, completely yet, but don't get sick. Yeah. I saw Margaret getting one, so it made me think about how everybody else was doing. Okay, so the only two requirements are is it continuous and is it differentiable? But the values of the function don't have to be equal to each other. So we look at that and we say it's polynomial, so it's continuous, it's differentiable. So that means that's all we need to know. So let's just write that out explicitly over here. So This is getting ahead of myself here. Doop. Okay, so question 1, can it be applied? So the questions are, is f of x continuous? Question mark, yes. Is f of x differentiable? And actually, I don't know if I really officially talked about the relationship between continuity and differentiability. So if I didn't, let me just look in the book and see what it says. There we go. So Theorem 2.1 says if f is differentiable at x equal, oh, that's the other way around. Okay, it says if it's differentiable, it's continuous. Okay. This is back in early in chapter 2. I'm not sure about continuity implies differentiability. Oh, the following statements summarize the relationship between continuity and differentiability. If a function is differentiable, then it is continuous. So differentiability implies continuity. It is possible for a function to be continuous, but not differentiable. Yeah, that's true. Okay. The only time that happens is if you have a cusp. The only time you can, so the function is continuous with a cusp, but it's not differentiable at the cusp. But all other functions, typically, if they're continuous, they are differentiable. But they're, there's an exception to the rule. Okay, so yes, yes, mean value theorem can be applied. So what you do for the second part, which is if the mean value theorem can be applied, find all values of c in the open interval such that this is true. So what you do is you're going to calculate f of b minus f of a divided by b minus a. So go ahead and calculate that. You'll need to figure out what. So plug in -3 into here, +3. See what you get. Actually, let's change it. Well, let me think about this. Let me just plot the function before you do anything. I want to see what this thing looks like. I have some vague remembrances of something. So I don't want the value of the function to be the same at the beginning of the end of the interval. That's what I'm concerned about. So it's x times x squared minus x minus 2. Plot this thing. So it's a third order polynomial. I need to change the view here. So what was it? What's the beginning and the end? Oh, it's definitely not going to be the same. Okay. So we're good. We can do that. So evaluate the function at -3 and +3, then divide by 3 minus, we'll let b equal 3 and let a equal -3. And see what that average slope is for that thing. One thing you could do is you could multiply this thing out. In terms of evaluating the function. So looking at the graph, it looks like it should be a positive number for the slope. Oh, you did finish them already. Was it the Cheetos or something? Yeah. The breakfast of champions. Does anybody eat the same thing every day for breakfast? So what is your breakfast thing? The people who eat the same thing every day? Frosted mini wheats, coffee, cocoa puffs, and what? Hot chocolate. Oh, that's lots of sugar in that thing. What's it? Yeah, I'm older, so I eat bran flakes and raisins. I put my raisins. I buy the raisins in like a big container like this, and I put them on top instead of buying Raisin Bran, because the thing about Raisin Bran is the raisins all go to the bottom of the box. So the first half of the box you don't have enough raisins, and the second half of the box you have too many raisins, and they also tend to be hard compared to um, ones that are packed in there. So they, sometimes I have French waffles on weekends, so homemade waffles. Okay, so what do we get for a slope? Maya, what'd you get? 7? That sounds right. Yep. Okay. Um, so what was f of -3? -30. And f of +3 was 12. Okay. Yeah. So what we have is 12 minus the -30 divided by 6. So that's 42 divided by 6, which is 7. Okay. So that's the value of the slope. So now what we want to do is we want to take the derivative of this expression, and it'd be easier, rather than using the product rule, it's easier just to multiply it out. So you'll take the derivative, f prime of x is equal to 3x squared minus 2x minus 2. So then what you do is you say, okay, what values of x does the first derivative equal 7? So you say 7 is equal to 3x squared minus 2x minus 2. So then you need to find the values of x where this go to 0. So it's not in the form that we're used to seeing, because, well, actually we need to find the values of x where this equals 7, but an equivalent thing would be to subtract 7 from both sides, and then find out what the values of x for that second order polynomial need to be for it to equal 0. That's what we're used to doing. So what we would do is we would subtract 7 from both sides. So you get 0 is equal to 3x squared minus 2x minus 9. So how do you think we ought to find the zeros of that? I guess we could try to factor it. I can't remember what the answer is. So, and there's going to be 2 solutions. They may not both be within the interval, but there are two solutions to that. So our options are just factor it using, just looking at it or grouping. You could use completing the square, which is kind of messy when if you divide everything by 3, and then you'd have 2/3 and 9/3, which is, so you could do completing the square. Usually if it looks something that doesn't look obvious, I would just use the quadratic formula. So why don't you use the quadratic formula? I'll write that out if you forgot what it is. Find out what the values of x are, which cause the slope to equal 7. So the quadratic formula is x equals minus b plus or minus the square root of b squared minus 4ac over 2a. I'm going to think if there's any easy way of doing this. I mean, just doing this. That's not going to work. What's the other option? 9. I could use 9 and 1. 9 and 1. That's not going to work either. Yeah. So I don't think what I was doing was looking at here, 9 minus 3 would give me 6. So that's not going to work out. And if you use 3 here, these are all the integer possibilities. So you could have 3 and 3, but you'd have 9 minus 3, which is 6 as well. So I don't think that's going to help us. So just plug it in there. It's kind of like with yesterday we were using the reference angle because we said in real life most things are not 30, 45, or 60 degrees. And it's the same way here. I remember using the quadratic formula a lot in engineering because typically if you had something that ended up needing to be factored, it wasn't necessarily a nice, easily factorable result. If you just randomly pick 3 numbers and put them in front of x squared, x, and a constant, the chances are pretty slim that it's going to actually work out to be a nice factoring exercise. So the bottom line is it's most likely going to be not easy. Life is not easy. Let's see what we get here. So I got 1 plus or minus the square root of 28 over 3. Let's just check to see whether that all makes sense. So what I'm going to do is I want to draw a straight line between the 2 endpoints, which I need to zoom out even further here. There we go. Okay. So the line between the endpoints, we could just use the point slope form of the linear equation. So we know the slope is 7. You don't have to normally do this. I'm just doing this to try to think about whether that answer makes sense or not. So you'd have y minus y1, which is going to be either 3 or negative 3. We'll use 3. So it's going to be y minus 3 is equal to m, which is 7 times x minus, actually that's 12, not 3. That's the y value. So that should be 12. Because what we have here is we have 3 comma 12. So you got 12 and you get that. So that's going to be y minus 12 is equal to 7x minus 21. Add 12 to both sides. So you get y is equal to 7x minus 9. Okay, so that's the line I want to plot. 7x minus 9. (7x minus 9) graph. Oh, what happened there? Must have forgot to put a. Oh, I used a colon. I don't know why I used a colon. I wonder what that does. I never seen that. Okay. So there you can see that that is the line that's connecting x equals 3, y equals negative 30, and x equals positive 3, and y equals 12. So that's the average slope. And it's saying that there are 2 points, one plus or minus the square root of 28 over 3. And so you can kind of tell it's going to be somewhere about right, maybe there, if you just eyeball it, and maybe about right there. So let's actually see what the decimal values are and see if these are even close. They're in the right ballpark. So you'd have 1 plus the square root, oops. So you'd have 1 plus the square root of 28, the whole thing divided by 3. So I get x equals 2.097, and if I change that to negative the square root, I get x equals negative 1.43. Okay, so I guessed that the slope is about that, about here, which is about negative 1.43, and I guessed about right here would have about the same slope as that, which is close to 2 points. So look, the numbers look reasonable just looking at the graph. You could confirm that you could doubly confirm it by using this slope and this point, calculate the y value associated with this point. You could find the slope of the line, the tangent line, and I could draw the tangent line, which had a slope 7 but touches this curve, and we find out the answer's right. So I think we did everything correctly. I'm paranoid today about making a mistake for some reason. So what is that thing? Oh, I'm not sure what that graph is. Okay. Okay. Yeah. So let's look at this one. This is going to be using the mean value theorem, but with trig functions. So it allows us to practice the stuff we learned the other day. Wow, this is a fun one. Oh, good. It's good. It's challenging. So what we have is this function 2 sine x plus sine of 2x, and we want to look at whether first, does the mean value theorem apply? And that function is continuous. The sine functions are continuous. And if you add 2 sine functions together, you get a continuous function. And it gives you the beginning and the end of the interval. So the beginning of the interval is pi over 4. The end of the interval is 5 pi over 3. So what we need to do is the same thing. We need to evaluate that function at the beginning and the end of the interval, then divide by b minus a to find out what that average slope is between x equals pi over 4 and x equals 5 pi over 3. Then we're going to take the derivative of that expression, set that equal to this slope that we calculate here, and then try to find the solutions. Okay. And it's not trivial, so we'll work through this together. This is just to give you an example of both using the mean value theorem but getting a little more detailed about trig functions. So go ahead, first thing we're going to do is calculate the value of the function at pi over 4, and make sure your calculator is in radians. Evaluate the function of 5 pi over 3, and then once you have the values of the function, calculate the slope. And let's plot, while you're doing that, I'm going to plot this thing. Just show you what it looks like. So it's, I already forgot what it was. 2 sine x plus sine of 2x. 2 sine of x plus the sine, plus the sine of 2x. And we'll graph that. Looks kind of like that. Let's set the limits here. So it's going to be pi over 4 to 5 pi over 3. And then we'll zoom out a little bit here. Wrong way. Zoom in. Okay. So that's what the function looks like. And what we're going to do is we're going to find the average slope between the beginning of the interval, pi over 4, and the end of the interval, 5 pi over 3. So the slope is going to be something like that. So it should be negative at least. That was why I plotted it. You should get a negative number for your first part of the problem. And like I said, just use your calculator to do the trig function stuff, but make sure you're in your radians. I'll give you a few minutes head start before I start doing it. But the slope is going to be some weird number. It's not going to be a nice even number. So the question is I have more caramels. Would you like me to bring some on Monday? They were okay, huh? Delicious. Delicious. Anybody have younger children who watch Peppa Pig? Yeah, they say delicious, don't they? Delicious. Martha sent me this picture. She went to the zoo, the Staten Island Zoo, on her trip, and there's a pig at the zoo. It's a small. Whoops, sorry. It's a small zoo, and the caption was, "It's Granny Pig" or something like that. I don't know, some Peppa Pig reference. Delicious. Okay. Does anybody get that answer? Yeah. Okay. So the value of the function at pi over 4, if we look at the graph, you can see here it's 2.4 something, 2.414, and the value of the function at 5 pi over 3 is negative 2.5 something. It says negative 2.6. So we're in good shape. Okay. So now what you do is you take the derivative of that function. So I need to find f prime of x. So 2 cosine x plus 2 cosine 2x. So the first one's easy, you just take the derivative of the sine. The second one you have to use the chain rule. So you're going to get the derivative of the sine of 2x is the cosine of 2x, but then you have to take the derivative of the argument, which is 2x. The argument is 2x, so the derivative of 2x is 2. So that's where the second 2 comes. When you watch your review for the test, you really want to pay attention to taking derivatives of the cosine or sine of or any of the other trig functions of something other than x. And the basic idea is whatever the argument is inside the trig function, when you take the derivative, you multiply the derivative by that constant. And I mentioned that in the thing, but that's, a lot of people would take the derivative of the cosine of 2x and they just say it's the sine of 2x. They forget to put the, the derivative of the sine of 2x, the derivative would be, they forget the 2 part. Instead of cosine of 2 cosine of 2x, they'll just put cosine of 2x. And there's enough occurrences of that in your test that you don't want to mess that up, so you don't get that wrong every time. Okay, so that's the derivative. So what you do is you set this equal to the value here. So you get negative 1.126 is equal to 2 cosine of x plus 2 cosine of 2x. And if you look at the graph, you can imagine, let's see, so this is the average slope. So there should be one solution maybe about right here. There's probably another solution about right here. There's another solution here, and there's another one there. So it looks like there are going to be 4 values of x in that interval that have this slope. Okay. So what was this? Do you remember the form of the equation that we solved the other day when we were trying to demonstrate the reference angle? It was 12 sine squared of something and then something, it was something squared. And you see here we don't have squared. And you really can't solve a trig problem unless they have the same argument. So how do you think, what do we need to do in this problem? The next step. How do we get 2x, cosine of 2x, into something involving just, it's one of those trig identities. And I think, oh, here it is, good. No, it's not there. Does anybody have their book? Hopefully they do. Anybody? Oh, Elias does. Good. Do you have that paper? You can just hand it to me. Yeah, okay. So if we look in our trig identities, we'll see that the cosine of 2u is equal to, there's 3 choices. And the choice that we use is the one that involves the the cosine, not the sine, because we want to get everything in terms of the cosine of 2x. So this is what's in your book. It says that the cosine of 2u is equal to 2 cosine squared of u minus 1. So if we plug that in here, you'll have negative 1.126 is equal to 2 cosine of x plus 2 times 2 cosine squared of x minus 1. So I'm replacing cosine of 2x with 2 cosine squared of x minus 1. So what I want you to do now is I want you to multiply that out and put it in the form of something times the cosine squared plus something times the cosine plus something, or plus or minus. We want to get it into a quadratic form. Okay, thank you. And the other day we were able to factor it just using simple factoring. In this case, we're not going to be able to do that. We're going to have to use a quadratic formula. So we're going to, it is kind of like a, you know, there's a lot to this. That's one thing about calculus versus pre-calculus. You can come up with problems that take you half an hour or an hour. Usually the pre-calculus stuff, even the hard problems didn't take you, well, they may have taken you a while, but if you know what you're doing, they don't take us a lot of time. But in this case, even if you know what you're doing, it takes time, but it's all the individual stuff that you should know at this point, or at least you should have experienced, seen it at some point. Okay. Hopefully somebody got that. So ultimately we want to solve for x, but this intermediate step, we have to factor this. We want to find basically what we want to find out are, if we factored this, the cosine of, we'd have the cosine of x plus or minus something times the cosine of x plus or minus something or plus something. We'd factor that, and then we'd set these equal to 0, those factors equal to 0, and the values of x where those factors go to 0 is the solution to the question, what are the values of x where this derivative equals 0? So what we're going to do is, a is equal to 4, b is equal to 2, c is equal to negative 0.874. So use quadratic formula. And really what we're solving is for these numbers. We're not solving for x, so I hesitate to use x even though that's what we would have used. Just use the assuming it, use x but then remember that it's not really the x that we're solving for. We're just trying to find out these things. We could say what we're really solving for is the cosine of x is equal to minus, we could do that, plus or minus the square root of b squared minus 4ac over 2a. I guess we could do that. Yeah, that makes sense. Okay. So what we'll end up with is two values of the cosine of x that will make it so that the derivative goes, or this equation works out. The derivative equals negative 1.126, and because for each value of cosine of x we have two solutions, so we'll get two solutions from this, from the plus or minus, and from each one of those results we'll get two values of x that will be solutions to the original equation. Let's see what we get here. Minus 2. Okay, so that's what I got. So the two solutions are the cosine of x equals negative 0.78 or the cosine of x equals 0.28. Obviously, these are not 1/2 or the square root of 2 over 2 or square root of 3 over 2. So that's when we have to use the reference angle method to figure out what the solutions are. And there's going to be two solutions. And they're going to be, you're going to choose the solutions that are in the let's see, the cosine is negative in the second and third quadrants, and the cosine is positive in the first and second quadrants. So next time, which will be Monday, we'll continue on this problem. Like I said, this is the interesting. It's not really that complicated. I mean, the actual math is there's just a lot of steps to it. You just have to, you got to check your work as you go through, and you just got to be methodical about it. But there's nothing deep inside. It's not like physics where you have this word problem, you don't know what to do. You know what to do, you just have to do it. It just takes a long time. You'll get to see all the things that we learned in the last 7 years, why we learned this stuff. Ultimately, it's used in calculus. So you survived long enough to be able to see that. So we'll stay in here today as usual. And oh yeah, there's. So I'm gonna go ahead and officially assign the homework today. So this is the homework for this section. None of them will be as hard as the one we're working on right now.